Morning, everyone. Welcome to this, the final plenary session of our 11th faculty conference. Glad to have you here this morning. We're quite pleased to have a keynote speaker who is going to give us some insights. We've been having very interesting talks all for the 3 days, and I expect no different today. I will not be here for very long. Our speaker is going to be introduced by Dr. Maroon Ferrat from the Department of Physics, and I will invite him now to come and introduce our keynote speaker. Would you make him welcome?
Thank you, Mr. Chairman. So, good morning, everybody.
Good morning, sir.
Well, it's great honor for me, next to the organizing committee, to be assigned the role of introducing Professor Mohammed Al-Ini in this very special occasion of the 17th anniversary of our institution with this very successful FST conference. Again, well, more than 750 research papers, most of them published in high-ranked physics journal, including Nature, Science, Physical Review Letter, Physical Review B, Applied Physics Letter, and so on. 705 research papers in physics is indeed astronomical number, which probably need at least 2 lifetimes to be achieved by an excellent scientist. The overall citation of those papers is 15,446, 3,417 during the last 5 years, with an H index of 58 and 29 in the last 5 years. The standard is indeed very high. I will not go again through the biography of Professor Mohammed Al-Ini, since this is already included in the program sheet. Instead, I will go through his other administrative responsibilities. Mohammed Al-Ini is Professor of Applied Physics in the School of Physics and Astronomy at the University of Nottingham, and he is also attached to Nottingham Nanotechnology and Nanoscience Center at the University of Nottingham, of course. He is an international postgraduate student tutor, an international postgraduate admission tutor, an international postgraduate recruitment, a Midland Physics Alliance Graduate School placement officer, and the first year course co-organizer. For the School of Physics and Astronomy, he is a committee member of School Management Group, Postgraduate Committee, Diversity Committee, and Learning Committee Forum. For the University of Nottingham at all, he is a committee member of Africa Middle East Strategy Group, member of the American Regional Strategy Group, Energy Technology Research Institute, champion for solar energy, and his presentation today will be about energy from the sun. His research activities are diverse, and I am going to cite some main interests of his research. This includes molecular epitaxis, this is a technique to grow thin films, deep-level transient spectroscopy, photoluminescence, and he is also leading several national and international collaborations. Maybe it is good for now to stop here and let Professor Al-Ini deliver his plenary lecture about subjects so important to Jamaica in particular and the world in general. So, Professor.
Well, first, let me just thank the organizers for allowing us to come here and speak to you. It's a great pleasure to be here, but there is a huge shock of temperature between the UK now and Jamaica, but it's nice to have a blue sky this morning. But first, I would like to thank as well, Farhad for introducing my research work. But I have to say, those 750, probably this much more now, it is not all written by myself. This is actually the result of many collaborations, both nationally and internationally. And this is really important if we really want to maximize your output. One of the best things to do is to collaborate with your colleagues within your school, university, and as well, worldwide. Because as we say, in Arabic, one hand doesn't count. You need two hands. Especially now, collaboration is practically part of the process for successful research activities. Okay, having said that, what I'm trying to do today is just to give you a flavor about some of the solar energy, how we can use it, when we can use it, and what are the main challenges in using solar energy to convert it back into electricity. That's what the whole thing is all about. So as you can see here, this is Nottingham. This is the campus in Nottingham. I'll say a few words before I start about the topic which I'm going to talk about. This is a photovoltaic or solar energy conversion to electricity. So for those of you who don't know Nottingham, remember the UK is a very small country. So but Nottingham is right in the middle of the UK. It takes about 2 hours from London. So anyone who is in the UK is most welcome to come to Nottingham. It's a very nice city. But those of you who don't know Nottingham probably have heard of Robin Hood. So when I go worldwide, a lot of people don't know Nottingham and say, have you seen the movie of Robin Hood? They say yes. So that's where I came from. So this is a statue of Robin Hood, which is very, very famous near a castle. But of course, Nottingham is well famous of this pub, this public house where you can have a nice beer and a nice food as well. This is actually the oldest pub in the UK. So we got quite a bit of history and a bit of things to do in this pub. But more interesting as well is called this green mill. So this actually is a mill. You think that you are in Holland. So actually this produces flour. Green was a miller, but his son becomes a mathematician. And when he was helping his dad, he developed these equations called green functions. Very, very powerful functions or mathematical tools practically to use in optical fiber telecommunications. So now it's a museum, actually, but you still can buy flour from that, still working, and that's what, so we got, as you can see, you don't have to go to university, becomes a very famous mathematician. So he was a clever guy, and that's what green functions are for. Nottingham actually has got 3 campuses, just to show you actually why internationalization is very, very important, not only for research, but as well to get people from different cultures, different countries to get together. So University of Nottingham has actually got 1 campus in the UK, 1 campus in Malaysia, and 1 campus in China. So actually there are staff from UK staff, we can go to these 2 international campuses and teach. But that's what they recruit international people as well, who can as well do work there. So we got 3 campuses. And I think they are thinking as well for having a 4th campus somewhere probably in Africa in the near future. So as you can see, it's really important, this internationalization thing. Now let me just start with my talk. Everything starts in the lab. You got a small desk or small lab and you do a lot of things. And if you think about science in general, it all is based on materials. We cannot do anything today without using materials. Whether we use wood, whether we use plastic, whether we use special materials. Materials are absolutely very important to do anything in our life. So all usually, either physicists or chemists, they use this table. That's the periodic table. It has got practically all the elements in it. So today I will only be talking about probably some of the elements in this what we call group 4, what we call silicon. Probably you all heard about silicon. But I'll talk as well about some materials which are from this group 3 and this group 5. So this is like practically you add metals like gallium and arsenic. You see here, you see gallium. And if you do arsenic, actually you end up with a new material system which we call semiconductor. A semiconductor. Because we all know we can have, for example, something which doesn't pass electricity is very, high, resistivity, like a metal. Like a plastic, like wood. It doesn't conduct electricity. You get metals which conduct electricity, like aluminium and so on, copper. But you got this very interesting material system, which are called semiconductors, which have got this behavior. They only conduct, under certain conditions, and these are very powerful, including silicon. But again, the most important thing is whatever you do in the lab, it has to be transferred to something you can apply. And this transition here from this basic research to applied research is a very, very painful one, especially for physicists. But if you think actually the major discovery, and the major discoveries who have led practically to some applied things are based on a physics concepts. If you think about today, about either electronics or optoelectronics, they are all based on some quantum device, on really pure quantum physics. Like if I'm using this laser here today, this red laser, is based on a quantum physics principle. If you got one of those fancy cars, light emitting diodes for your reversing car, those are based on a quantum physics principle. So if you think about it, physics actually is applied a lot. But to really find a niche for any new discovery and to make it applied is very, very difficult. Today, hopefully, I will show you one of the biggest one is, apart from the laser and apart from the transistor, which changed our life, solar cells could be the next big, things in our life. And that's what I'm trying to cover today, based as well on some quantum physics. Let me just start, just to give you perspective why solar energy started first, okay? In space, we don't have a plug to power equipment. This is the first satellite, the Russian satellite, Sputnik 1, which went orbiting around the Earth. Right? And of course, you need some power there to power these electronics in there to make it go round. So you need something to generate energy or electricity to make it go round. Okay? And I'll come back to that later. So a few years later, practically you got the Vanguard one from the US. This is as well another, what we call first solar powered satellite. It was really small, around just 1.5 kilos. And it has a power only of 5 milliwatts, a very, very small power. But it was powered by these little things in here, okay? As you can see, it's only about 1 centimeter by 1 centimeter. So this was a solar-powered satellite, and this was a solar cell. So this started around late 50s, okay? Because you needed something to power. If you want to do anything in space, you need something to power them, and that's how solar energy becomes really important for space applications. And as soon as that actually satellite went around, the New York Times really picked up on this, and it says, vast power of sun, although here I'm just saying it's about 5 milliwatts, so it's very small power, but the New York Times picked up on this, and what it says, vast power of sun is tapped by battery using sand ingredient. Sand. Because silicon, actually, those solar cells, those small 1 centimeters, is made from silicon. And silicon, which is a semiconductor, actually you can make it from sand. So they thought, well, we've got plenty of sand. We're going to practically generate a huge amount of power, to power not only space, but as well, on Earth as well. Okay? And this becomes practical, as you can see, the main power source for a space application. But it was very, very small. Now, I'm going to divide my talk in a couple of sections. One mainly for application on Earth, and maybe as well on space. Because these are the two major applications, as you can see. But just let me give you some perspective about why we want to use as well solar energy on Earth. Look, this is a map. As you see, the redder it is, the more sun you have. If you look here, Holland is in here. It's a bit more green than red. Okay? And as I say, if it works in Netherlands, or in Holland, it will work everywhere. Because I will show you what Holland does. It does not have enough sun, as all these you guys, you are somewhere around here, you're blessed with the sun. Look at the US, look at Africa, completely look at Australia, look at part of South America as well, a huge amount of sun, but we're still not tapping on it. Countries like Germany and Holland are tapping on this energy quite successfully, despite they don't have sun every day. So just some few applications. Anything we could help make a tremendous change in our life, not only actually, for the global warming and so on, but it will help practically the environment. So you can see here, I'm not sure, I haven't visited Jamaica a lot. I just arrived yesterday. But in Europe, actually, now we can see a lot of roofs have got solar panels to power some houses, right? You can use them in many different applications. Even here, although I'm showing this bit here, you can use them in parking space. Now in the UK, practically all the parking meters are powered by this small panel. So you don't have to dig holes, you have to put power cables, so on. You put a panel and you can move it wherever you like. It's simple things, but you can see how it makes those small little things can change our life. Let's just give you about the global development in terms of photovoltaic or solar energy. If you look for, mainly terrestrial applications, from 80s to today, you see how we changed the sunlight to practical electricity, the efficiency, okay? I will come back to that later. Efficiency means that what you put in and what you get out. Usually, we are all greedy. We want to put 100% and we want to get 100%. But unfortunately, in solar energy, you put 100%, but you don't get 100%. You get much, much smaller than that. And depending which material system you use, you will get higher with some, lower with others. But depending on the application, you choose what you want to do. But I will show you some example later on. So this practically doubled. The efficiency over these 30 or 40 years has doubled. You say, I'm going to give you some more example later on. If you look at the prices, they're practically decreased. Like everything in life, when you start making them in big volume, the price will drop. Why I don't want to put solar panels in my panel? Because it's still a bit more expensive, but the cost is going down all the time. But you look here at the, the total annual market and the total capacity now, it has increased by a huge amount, 10,000. You see, because people now are starting using this in their roof. But of course, there are some incentives from our government, like in the UK, if you put this, you get some incentives. And the energy you don't use, if you must, overproduce, you feed it back to the grid, and you get paid for it as well. So this is some more incentive. That's why this capacity is increasing. And you can see here, this is a very, very small amount. The photovoltaic, in terms of contribution to the global electricity, okay, we can generate electricity by different means. I'll tell you later about it. But now it's only about increased by 2%. So it's a very small amount. But I'll show you the prediction for the solar energy as time goes by. So from today, what we want to do now, from today to as soon as possible, okay? Practically, we want to use this energy. We want practically to increase this efficiency by a factor of 2 as well. Because increasing efficiency is extremely hard. I will show you some example later on. Of course, if I want to tempt you to buy this system, I want to still decrease the price. And the expectation you want to decrease by at least a factor of 3 to become more attractive to people, for example. And of course, we want really to increase this capacity and contribute to this production of electricity more than 20%. I told you it's only 2%, and we want to increase this to 20%, and how we're going to do it, I'll show you later. Okay, if you look at this diagram, it's the global capacity, okay? That's in gigawatts, okay? This is as a function of time, but you can see, it didn't pick up in 2000, practically hardly anyone used solar energy. Okay, for application, just think about houses. I mean, it's very more, attractive. But look with time how this is going exponentially, okay? Because as I illustrate to you, the price is going down, the efficiency is going up. All these practically encourage people to change, to different energy production. Let me show you this diagram, because this is practically for people who are working practically on solar energy to convert sun the solar from the energy from the sun to electricity, this is the thing you want to look at. So here, practically, I'm showing you the efficiency. As you can see, the efficiency here the maximum is about 50% as function of time. And I'm using different kind of material system. These are all different material systems, as you can see here. If you look at this material system here, which I'm going to explain in a bit, you see its efficiency with time has been increasing dramatically year after year. But remember that advert from the New York Times about silicon, saying that it's going to practically produce a huge amount of power. Unfortunately, silicon is somewhere around here. Can you see this silicon? So you can see silicon. The problem with silicon, started about an efficiency about 12%, but even now, after many, many years, it's only about 20%. So the increase is only about 8% over 30, 40 years. So you see, it's not easy to increase efficiency of these things, because what you want to put in, you want to get as much as out as you could. Okay, so silicon has been struggling. And of course, we know silicon, if you open your laptop, if you open your mobile phone, all those electronics are made of silicon. It's a huge, silicon is huge in microelectronics, but as well is huge in photovoltaic, but its efficiency is not good enough for some application, especially for space. I will explain that later on. These are the material systems which really, if you want to go to space, to look at, because the efficiency is nearly about 40 to 50%. Okay? But there are many new material systems are coming, what we call the oxide material system, the organic, and there are many new materials. Efficiency is small, but they got different niches, depending on what you want to use. Okay, let me just show you in terms of the technology we use is mainly for terrestrial application. We mainly use silicon because it's a bit cheaper than other technologies. And remember, if you want to put this panel on top of your roof, all right, you want a really good cost. Okay, and this is what we call. There are different, actually, different kind of silicon. What we call monosilicon, amorphous silicon. There are different kinds. How pure silicon is. And that's what you made this solar cell a bit cheaper in order. Even though efficiency is not very high, but at least you make them a bit cheaper and affordable. Just here to give you some, some few ideas where this different silicon is used practically. This is what we call monocrystalline. That's mean pure silicon. This is what we call multicrystalline. It's amorphous. It's not as pure as silicon. And there are many used practically in roof. On top of these houses. But there's another kind of semiconductors which is called cadmium telluride, which are very thin films as well, and they have got an efficiency about 16%, not as good as the silicon, but they are as well used for different applications. Here, the concentrators. Okay, this is what we call the multijunction 3-5. Remember that table I showed you, the group 3 and the group 5. I'll come back to that again, and this actually This material system is from the group 3 and the group 5 of that table. This is actually the one which produces a very high efficiency. So you can see, if you want for some application when you need high efficiency, and there are some applications where you need high efficiency, I will show you later on, you have to use this practically kind of material system in order to achieve very high efficiencies. What is a silicon, what is a solar cell? It's a very simple device, extremely simple device. And I'm trying to explain because I'm not sure about the audience. Maybe you are from different kind of background, from physics, from engineering, but just let me just show you as simple as, I could. So actually, it's the same concept, whether it's a laser, whether it's this laser I'm using to generate light, or it's a solar cell is exactly the same device, but they only work in different ways. So in this device, which is the solar cell, all you do is shine light from the sun on this piece of semiconductor. And what you usually, when you do that, practically create a charge. One is an electron, and one is a hole, which one has got a positive charge, one has got a negative charge. Okay? And what you do is just separate them. And when you separate them, you created a battery. It's like the battery I'm using to generate power for this laser. All right? So this is how it works. Practically, you just create these charges, and you separate them, and you store them in a battery. And then when you want to use it to generate electricity, you just connect it to a circuit, practically to a light bulb if you wish, to just have these charges going on. So it's a very simple device. A laser works differently. So the laser, you don't want to actually to separate the charge. You want them actually to recombine. And when they recombine, they give you a photon of certain energy. Like this one, you give you in red, you can have blue, you can have green, you can have different colors. So it's just the same, you generate these charges, and whether you can make them recombine or you can actually separate them. They work in different ways. However, to achieve these very high efficiencies, it's a very, very hard work. You have to play several games in order to really improve the performance of these solar cells. And I don't want to go through all of them, but it's quite complicated. The architecture of this device becomes very, very complex, in order to really improve the efficiency. Just simple example, when you shine light to a piece of materials, not all the light is absorbed. Part of it is reflected, right? And you lose it. If you lose it, that means your efficiency will decrease. So you have to play a game how I'm going to capture all these lights. And this, for example, one of the ideas to have these corrugated surfaces in order to trap the light inside. You don't reflect, for example. So there are different concepts how to improve the efficiency. But unfortunately, it's not the purpose of this talk, just to give you an idea that is a very, very painful idea. So here, as you say, you need a lot of innovations, a lot of blood and sweat and tears. As I told you, even with silicon, which is a very well-established semiconductor, it took about nearly 40 years to go from 12% to 20%. 40 years, so it's an 8% efficiency improvement. It's a hell of a lot of work to do, and I would say a lot of sweat, and a lot of new ideas and new concepts. But this is how we went from this low, from say 12% to around 20% by using different approaches. I don't want to go through all these, but remember, you want usually a low-cost ideas, because cost will drive you. But if you just look, the cost will come down. Just look at all the old TV. We had this big, a tube, right? It used to generate so much heat and it takes so much energy. Look, we all now got flat screen, But if you remember a few years ago, those flat screens were extremely expensive. Now they come down in price, and then I haven't seen one of these tube things for many, many years. But the cost will come down. But today, I will mainly show you the concept of this tandem or this multi-junction, how they work. And this is a beautiful idea, how to really improve the efficiency of these solar cells. I will mainly concentrate on this one today. Let me I'm just reiterating again about the use of this solar energy. Just give you an idea, more than 100 countries back to use solar energy in 2010. And this is increasing, as I showed you, the number of people, countries and, are increasing. In 2009, just give you an idea, it was about 20 billion. This becomes actually more than doubled 3 years later. And this is increasing, just to give you an idea, those are all data, but this is increasing, as I showed you with that diagram, how it's going exponentially. So the same thing applies in the market. This is going exponentially too. Because there are so many uses now, to replace those cables, to use different, solar energy to generate electricity in many different areas. But at the end of the day, probably UK is based mainly on coal, and then we practically all around the world are basing the cost per watt, which is the cheapest is by coal. Okay. So here you can see, so practically this is an old data, but just to show you. So this is the cost in dollars, as function of time, and you can see how this is becoming lower, okay, all the time. The threshold to compete with coal, it should be around $1 to $1.5 per watt, okay, because that's how much it will cost you if you use just coal to other different energies. So, but this cost is going down, and that's what you have to keep in mind. You see, because you have to compete again with different energy sources. Now, this is why I think, I switched from the application in terrestrial application to space. Because space is really important, and you need a means to produce energy. All right? So look at what I've told you earlier. The solar energy starts actually, as you can see, 1 centimeter by centimeter. That's what it starts, all this use of energy, of using the sun. And this is the panel, as you can see. But look, 40 years later, right? Look at this panel. I'll show another example in a bit. These all the panels which you need to power these stations. We've got 1 or 2 stations, up in the space. Look at the size. But I'll show you this. So practically, these kind of things, I will show you the reason why we want to improve the efficiency, especially for space, is to improve the efficiency of these solar cells. And I'll show you why. The reason why we want to improve this efficiency for space. Now, look at this space station. Look how many panels, the similar one that we're using here. There's 1 panel. But look here, how many panels you are using to power this station. Because there are huge equipment there, many things are in there, and you need a lot of power to really power those things in space, right? So why do you want to improve the efficiency of those solar cells? For 1 reason. So can you imagine if I need, so for example, all these panels produce, say, X watt, a certain energy, using a material which is probably 12% efficient. Yeah? X watt, I need this size, say 16 meters, when I use, for example, silicon to give me X watt. However, if I use another material, say gallium arsenide, this group 3 and germanium, with efficiency of 18%, that's 6% efficiency, I can decrease these panels by 6 meters to 10 meters, right? If I use another material system with different system which can produce an efficiency of 40% to produce the same power, I only need 5 meters of that. So this gives you an idea about the size of this panel. By increasing the efficiency of the solar cells, say going from 12% to 40%, you would practically, cut the size by 1/3. So this is the reason. And of course, when you do that, especially for space, this will apply again for terrestrial application. If you increase the efficiency, you need smaller panels. You don't need the bigger panels. So here, practically by reducing the size, you reduce the weight, you reduce the cost, and so on. So this is the reason why we want to really improve the efficiency further and further for this system, not only for space, but as well for terrestrial applications. So there is a need for efficiency because the state of the art now being used is about 30%. And how we can use the different structures or different devices really to improve this further than 30%. And that's what I'm going to try to explain as simple as, at least for the space application, and how we can improve that. But here just again to show you this is the group 3-5, and it's been improving all the time. So that's what I'm going to practically concentrate on, you see, and how we can take this a bit further on these lines. How we can do that. It's actually going, it's the same one, but just here, just show you the high efficiency group 3-5, but they are very expensive. You got, the high market or the high throughput as well. It's the low-cost silicon, because silicon is, of course, much cheaper than this material system. Okay, and you have practically to use something which is simple. You say simple and cheap. Okay, and if you want to change this, so depending what you want to do, you choose the right technology in order to achieve what you want to do. Just let me give you an idea. So to have an idea about what it means improving the efficiency in terms of power. I just took a simple example. Say, for example, in 2010, there was about capacity of 18 gigawatts. That's the total capacity in the world, 18 gigawatts, okay? If I have to use or improve the efficiency of those solar cells by just 1%, okay? Just by 1%, I use different technology which I can increase it by 1%. Say, for example, it was 10%, and use different technology to give me 11%. That means I can save about 1 gigawatt. Okay, but improve it by 1%, all right? So just to give you an idea, what does it mean 1%? 1 gigawatt, so that means 18 million 60-watt bulbs, okay? So you can see, especially for those who are doing research on solar cells, every percent counts. It's very hard sweat, hard work to achieve, improve the efficiency of these solar cells. Okay, so again, as I said, just to give you an idea, because silicon is one of the basic material or the basis for microelectronics. But for solar energy, unfortunately, it hasn't performed as good as those 3.5 using different kind of silicon, but it stacks around 20%. Now, let me just say about the silicon, the use of silicon, okay? Even if you want, even if it's a lot of it, as the New York Times, you got, the sand, you can just use sand, they've got plenty of sand, you say. But of course, silicon as well is used in microelectronics. So if you look at, the metric ton as function of time, for the semiconductor electronics, as you can see, this is what has been used a lot, okay? This is actually the total production of silicon, okay? It's all time. The production of silicon is more than what you use, of course. Now, if you want as well to use silicon for the photovoltaic, all right, you're going to be big pressure on producing pure, pure silicon, for example. And you can see already there is a problem here. As you can see, we won't be able to produce enough silicon to fulfill both markets. The electronics market, which we know, and the photovoltaic too, okay? So this is going to be a challenge of making more silicon. Even if we've got plenty of sand, it's not easy to make more silicon for these applications. So this is a bottleneck. So now let me just show you how we can improve the efficiency of, for example, the existing solar cells which are used for space. So this is practically the energies of the solar spectrum. You see these energies which are in the sun, okay? So you can see the energies, I use them in electron volts, okay? So you can see here from 0.4 electron volt, that's UV. You don't see it with your eye. And here, for example, you got ultraviolet here, and of course you got some visible here. So you got all the visible, the UV, and all the near infrared things, okay? And you see what you want to do, you want to harness all this energy. You want to convert all those energy in the sun to electricity. That's what you want to do, okay? How are we going to do that? So what you do, as I said, you have to choose a material system which can absorb those energy. But unfortunately, we haven't got a single material system which can absorb all this energy. There's not a single material system who can absorb all this energy. So you can only absorb, a portion of that spectrum. Okay, like this one, I use this yellow one to absorb only this region of the solar spectrum. So if I want to use actually a different, absorb that, because remember, that's what I want to absorb in order to create this charge, the positive charge and the and positive charge to make a battery. So what I have to do, I have to stack different material systems one on top of the other, and each one will be tuned in terms of energy to absorb that part of the spectrum. So you can see this red one will absorb this red of the spectrum, the yellow this part, the blue absorb this part. So that's what we call the multi-junction. So each junction or each material system will absorb that part of the spectrum in order to really improve the efficiency. Because otherwise, all that energy, if I use only one junction, all this energy is lost. I don't absorb. That's what I don't get 100% efficiency. It's lost. You see? So that's what I'm trying to find a way to absorb all this energy to convert this electricity. Of course, having said that, it's not as simple as that. It's much, much complicated how you design your device. It's much more complicated. This just gives you a cross-section of the kind of the device, which is based on these three junctions here, practically. But to really practically make a useful device, there are a lot of other parameters you have to take into account, which is beyond actually my talk, but just to show you how difficult it is. That's what you call the top cell, the middle cell, and the bottom cell. And for each cell, there are many different layers in there who play different roles to improve the efficiency of the solar cell. So it's much complicated. And this actually what we call the three junction, and this is what we call gallium indium phosphide, gallium indium arsenide, and germanium. So there are three different materials, but they are all matched. They have got the same property, their properties are about the same in order to really stack them one on top of the other. And here you can get an efficiency of around 40%, but that's in the lab. When you transfer them actually to big panel, the efficiency will drop to around 33%. There's other different parameters. Making a device in the lab and scaling this up is a different story too. So, as I said to you, this is very, these kind of devices are very, very expensive because they're used in space, using a special material system. The way you grow them uses expensive techniques, and that's what they're expensive. So, one way actually to reduce the cost, because the bigger the area you use, like you've seen on those panels, on the top of the roof of houses, use a lot of material. But if you can reduce that material system with high efficiency, therefore you can really reduce the cost. Just show you here about this, what you call concentrators. In my time when I was young, we used to play with lenses. We put, a piece of paper. If you expose it to the sun, nothing happened. If you use a lens and you focus that lens on the paper, you burn the paper, because you are practically concentrating a huge energy on a very small point. So this is the analogy with this. So practically I can reduce this size to a very small size and use a lens really to concentrate this energy on this point. And that's one way we can reduce the cost of these solar cells, because we reduce the size of the material practically, but use a lens. It's just a normal lens. But as well, you're adding something to another system, but you are having a trade-off between costs as well. And this, you can see them nowadays in many, many different. Spain, you can see them quite useful now, actually. You see they use this parabola, and they can practically focus, the sun of light to generate high efficient solar cell. Again, as I said, this is actually the multi-junction, as you can see, by using. So here, just showing 2-junction, 3-junction, but going from the 2-junction to 3-junction, you see, it has improved a lot. So that's what you call the third generation of solar cells, the 3-junction. There are 3 different materials in order to absorb those energies from the sun, okay? But the same thing with silicon. We don't produce enough of it, although we have a lot of sun. There's not a lot of capacity. For the group 3, it's even bigger problem, okay? Because we use gallium, as I showed you, we use indium. But unfortunately, if you look here, practically, the different material system and the kilotons. So in the blue, it's what we produce, and it's what the world reserve. So you can see we haven't got enough gallium, okay? You see, we haven't got enough indium. So even with those technologies, you won't practically fulfill all your energy requirements for some application. Maybe for space is fine, because we don't have enough, many space stations, but this probably will grow in the future. You see, but if you use concentrators, for example, you can use them, on Earth as well, because you reduce the cost, and you don't use a lot of material too. So there are some issues as well, what we have and what we can produce, and how we're going to use them even for this material system like gallium, indium, and so on. So there is a small reserves worldwide. Now, look at the projections for generating electricity, practically as function of time. We have many different ways to generate electricity. You take France, 80% of the energy is produced by nuclear, right? Okay, so nuclear is the favorite for some countries. Of course, it's clean, but when you got a disaster, it's going to make a big mess, not only where it is, what the plant is, but worldwide, right? You got coal, for example. You got many gas, oil. You got wind. You got tide waves. In the sea you can see this. All of these are practically generating electricity. Okay, and this is the projection for all these technologies. But the projection for the voltaics is what the people projecting. So practically, that's what I was saying. We need at least 20% increase as soon as possible. You see, because this is what all governments now are practically looking at. And sometimes, actually, to be honest with you, it's not the technology, it's the politics of this, which practically limit the use of the solar cells. Because some of these big energy companies, oil companies, they don't want you to use, for example, oil. You see, they want you to use oil rather than electricity because of their own, their own interest. Okay, so there are a lot of lobbying, especially in the US, for not using the photovoltaic, but using oil, for example, or other technology, because it's like, for example, using water in your car. You see, if you can use water to run your car, a lot of these companies will go bust. You see, so it's not the interest, for example. Okay, so photovoltaics is there, but sometimes it's not only the science, how to apply them, but it's the politics behind it as well. So now let me just give you one simple example. by looking at the fourth junction, what we call the fourth generation solar cells. The third generation have got 3 material systems. And just give you an idea how we can really do it by using fourth junction. And this took a lot of time, a lot of effort, because it's all how we can actually improve the properties of this material system. There are some new material systems, and when you stack them one on top of the other, you got a lot of challenges. You see, because they behave sometimes differently, and they create a lot of problems. So here's the idea how to use many different material systems to fully match the solar spectrum. In other words, to maximize the efficiency of the solar cells. Here what I'm going to do, I showed you for the 3, I'm going to use a 4th junction, but I have to pick up that junction very, very carefully, and which practically match. It's just like sandwich structure. You see, you put one on top of the other, but they have to match. You see, just a simple example. If you want to heat, if these things get hot, if they go to different thermal expansion, they're going to expand at different rates, and then you're going to have cracks and so on. So they have to have some kind of properties which are similar to each other. And that was the challenge. How can we find different materials who have got the same properties to stack them on top of the other? Very big challenge. So here we got the state of the art, efficiency about 33%, they are in production. How I'm going to improve it by adding another junction. So the energy I'm absorbing now for those junctions which are used in space, that's the energy which I'm absorbing. This energy about 0.7, 1.4, energy and 1.8, because all these materials, the 3 materials are really matching together. So the idea is to find here another material system which absorb 1 electron volt. Because you can see it's a big gap between 0.7 and 1.4. So the whole idea is this magic material system called 1 electron volt material system. And if you look at 1 electron volt, this actually is a peak in there in the solar energy. And that's what you want to peak that. Silicon does it very well. That's what it peaks mainly because its energy is about 1 electron volt. But for the 3.5 it was difficult to find a material system which has got 1 electron volt energy. It's a very big challenging, and the big energy is this energy here as well, which you want to absorb. And the prediction was that if you find this 1 EV material system, you can increase to 50%. So can you imagine going from 33 to 40%? It's a huge jump. But remember the analogy I give you, what 1% mean in terms of energy. It's a hell of a lot. So it will be a very big jump. It will be more than what silicon did in 40 years. So here you are, just showing you here, this 1.8, 1.4 EV which we have, 0.7, and I'm going to find this 1 electron volt material system. How I'm going to find it? It's a lot of physics in it. I don't want to go through all of it. But it's been actually just discovered absolutely by chance again. Nature seems to spark something at you and just say, hey, you need my help, I'm going to help you. So look here. So this is the energy of the energy of semiconductors as a function of the size of the crystal. That's the size, how big the crystal. Because if you take, say, for example, this is called gallium arsenide, it has got the size of this crystal about 5.6 angstrom. If you take indium arsenide, another group 3, the size of the crystal is 6 angstrom. I remember 6 angstrom is 10 minus 10 meters. It's a very small difference in the size of the crystal, but it makes a huge difference in terms of strain, because they have got different sizes, and if you put them on top of the other, they create a lot of strain. Okay? So what's usually here, because here you got indium arsenic, indium gallium arsenide, this one's got about 0.5 electron volt, this one got 1.5, but when you add gallium to this, so what the energy does, it goes this way. It increases, all the time it increases. Okay? And if you look for many different systems, all time, if you want to go, for example, from indium antimonide to this material system, for example, by adding aluminium, the energy goes up all the time. Adding more material aluminium, it does. Nature gave us something different. So here's gallium arsenide, here's gallium nitride. I hope I can just explain as simple as I could. Gallium nitride has got a large gap, so this produces blue. If you heard about the Blu-ray disc, they use this material system because it produces blue light. Okay? And we know we can actually produce blue lasers which can emit a light in blue. Right? But here what's happened actually, what the people found, that if you add nitrogen to this gallium arsenide, actually it doesn't go this way. As all this material system actually decreases before it starts increasing. By putting small number of nitrogen into this gallium arsenide, the energy decreases before. And the energy actually of gallium arsenide is about 1.4. I'll show you. If you see here, gallium, sorry. If you look at the energy of gallium arsenide, it's about 1.4 electron volt. So by adding nitrogen, what has happened, I can decrease this small amount of nitrogen. I can reach 1 electron volt. That's what I'm aiming for, right? 1 electron volt before it increases, okay? And I will show you what it means by adding a small amount of nitrogen, what it does to this energy. So let me just, I'll skip this one. Sorry, maybe not. Okay, so what's really happened here? So here you see it's gallium arsenide, the group 5. So what you're trying to do, you're trying to replace this atom arsenic by nitrogen. But here as well in this table here, this is a smaller atom and this is a bigger atom. Because this, the size of the atom goes this way, it goes this way. So by adding nitrogen to this material system, it means that you replace some arsenic atoms by nitrogen, you're going to decrease it. But you're going to see you're replacing a bigger atom with a smaller atom. So you're going to have some problem in terms of properties of this material system. That's why it was very difficult to really make. But there was another idea as well, how to replace a smaller atom arsenic by a bigger atom, which is bismuth. So now you do the same thing. And then actually this is what we call them dilute nitrogen or bismuth. You're just replacing that arsenic atom by either nitrogen, which is smaller, or by bismuth, which is bigger, in order to reach this 1 electron volt material system without actually changing the properties or the size of that crystal in order to match the other one. And that's what we can have this combination. We can add bismuth, a certain composition, nitrogen, or actually we can co-dope them, add both nitrogen and bismuth, and we see what's happened. And it's really interesting what's really happening in terms of physics. And I've just shown, today I'm going to only show you about what's happened for the solar cells, but there are as well many other applications, mainly for the telecommunication, which could be another talk exactly by how to use this new material system to generate long wavelength lasers very cheaply as well. So, what's happened to the properties of this gallium arsenide, which was 1.4 electron volt? So for every % of nitrogen of bismuth you add, you decrease this bond gap or this energy by 0.1 eV. So remember, I've got 1.4 eV. I want to go 1 eV. I only need 4%. Very small amount. That's what we call them dilute. Dilute nitride or dilute bismuth to reach 1 eV. Okay? And this was practically was the big challenge. Okay? Again, when people found, including ourselves, we found this, all right? The problem is, again, replacing, when you grow this material system, replacing arsenic by a smaller atom or bigger atom, the optical and the electrical properties are very different than the gallium arsenide. Although the size is the same, but the properties are very different, and they are growing in a different way to produce them. So there was a lot of hard work actually to really optimize those properties, both electronics and optical, in order to integrate them into the the 3 junction in order to have something useful and increase the efficiency of the solar cells. I don't want to probably bore you with this because it's much more physics. You see, this is just the energy of this, because usually this energy I've been telling you to absorb, that's what you call a forbidden gap. You see, so just look, these are what they call the conduction bond, the valence bond, and usually when you shine light, practically you just use this forbidden gap, and this what is 1.4 electron volt. So by adding nitrogen, what's happened, you practically this energy here drops to this point. If you add bismuth, what's happened, this valence bond goes up. So they affect this nitrogen and bismuth, they affect the electronic properties for this gallium arsenide in different way. One decrease the bond gap, the conduction bond, one increase the valence bond, and therefore you can tune this energy as you wish to reach this 1 electron volt energy system. Okay, so this is actually how it can be explained both by theory, you say, what's happened, because you just introduce some states, electronic states, which can break this, this electronics bond diagram of this semiconductor. And this, the people who started in the lab a few years ago, including ourselves, it was a hard group. You can do these things in the lab, but if you want to scale them, it's really hard. Because the properties, you see, having an efficiency in the lab and having an efficiency which works in different environments is completely different. So actually, one of my colleagues, you know, in Houston, Alex Rundlich, they made this actually, and they had a patent on it, you see, but they just made actually the proof of concept of this material system. And those days, I think they were about 40% efficiency of this solar cell, which is actually including this one electron fault, 4-junction solar cell. So this is just actually a transmission electron microscope cross-section to show you the different layers. It's quite complicated. Okay. About 9 months ago, a company actually in Germany actually are now mass producing this 4-junction cell, which have got about 42% in a very large scale. So these are now in production, but not used in space, of course, yet, because, of course, it's not easy to replace what is in space now with new technology. It costs you more money. You wait until it dies, and then you can transport them. But they are in production. And all these techniques, all this material system, including actually this laser, or your light-emitting diode in your reverse, in your car for the reverse light, or your transistor in your mobile phone, you see, all grown actually by these techniques called molecular beam epitaxy. Actually, this is one of the first MBA system in Nottingham. As you can see, I didn't have really too many white hair. You see, this actually was in 1985 when we actually, the UK invested a lot of money in the UK to buy these techniques which can actually produce very thin film. By thin film, I mean in the order of the angstrom. So remember, 1 angstrom is about 10 minus 10 meters. So 1 meter divided by 10 to the 10, that's what an angstrom. So this technique can actually allow you to have this very thin, very accurately. These are the production systems. So these are the systems which actually produce these transistors in your mobile phone, or these lasers, for example. They are much, much bigger and, you know, and produce many, many wafers per month than this, you know, research machine. And this is what's called molecular beam epitaxy. It's just practically a simple technique. You know, you want gallium arsenide semiconductors, so what you do is just evaporate gallium, evaporate arsenic, recombine on a substrate, and you got a thin film. But the technique is, this kind of deposition is made in a very ultra-high vacuum conditions. That means the number of foreign atoms in that space, in this space here where we do the growth, for example, is practically zero. You only have the atoms which you are evaporating. It's like, you know, in outer space, you know, you got less and less molecules. That's exactly what we do on Earth. We pump all those, we remove all those foreign molecules, and we have only the ones which want to evaporate. So this was very expensive, £1.5 million in 85. So this was a big money in those days. The cost has decreased, but this machine actually produced about 200 PhDs over the time. You see, because quantum mechanics, all the principle of quantum mechanics could not be proved, because we didn't have any technique which can make this film very thin. Thin, which means they are in the same thickness as the wavelength of the electrons, in order to have this quantum phenomena. So this is the only technique which practically allows to demonstrate quantum physics in real life. What these devices, all the theory we learned in our physics courses, we can demonstrate them, you know, including this laser, which is a quantum device too. So I don't want to bore you about the environment. I think you know that using something clean, it keeps our Earth clean. Of course, I think, you know, if you look in terms of labor and business, as I said, because this is a very, very, going exponentially, and photovoltaics is one of the top priority in every government, how really to switch to renewable energies. So probably it will produce new industries and new manpower. So what I'm saying, if you're a PhD student, probably you should think about how to really to go to this photovoltaic field, because this is something for the future as well, in terms of jobs. So this is just a video, if you want to watch a video practically about solar energy, how we can grow them, how we can make them by using this technique. There's a link there where you can see actually how we do it. But just to conclude that efficiency improvement in photovoltaics are still ongoing. We still try to improve it. Ideally, we want to have 100% efficiency. That means that we absorb everything. But it's going to be very hard. But for the 3.5, it's been actually going, increasing all the time. So that's what people are thinking now for the 5th junction. You say how we can make the 5th junction to absorb more energy from the sun. It's not anymore a curiosity in the lab. It's a multi-business dollar industry. You see, so it's a huge, in terms of industry. And this molecular beam epitaxy has been playing a huge role, not only for solar cells, but many quantum devices. Actually, there is a philosopher which is actually from Australia. He called this now the quantum age, because every device you use nowadays is based on a quantum phenomena. As I said, whether it's a laser, transistor, or solar cell, they're all based on a quantum phenomena. So we are in the quantum age. We just probably don't, know it. Even in UK, in my department, my students, the 40th students, they still don't understand or know how physics is applied. It could be another lecture, how we can apply physics. And if you think about it, it's all basic phenomena. We all are using physics actually for all these devices. So physics is part of this all, of course engineering is important, but physics starts with physics and it goes, up. So it's, as you can see, photovoltaics is part of this new, I would say new trend, which are very, very important. And I hope, some countries will take advantage and develop this kind of technology for the future, especially those who are blessed with the sun. So I would like to thank you for your attention, and I'm happy to answer any question you might have. I might have gone through some concepts too quickly, but I'd just like to explain them as simple as I could, but happy to meet with you, and we go through some details as well. Thank you very much.
Thank you, Professor Henny. Do we have any questions, for Professor Henny?
Dr. Henny, very good talk.
Thank you very much.
Informative. I just like to hear your comments on the recent 3rd generation solar cell made by the Michael Gradual. You must have heard.
Mm-hmm.
And he announced recently that tandem perovskite and silicon can give you 30% efficiency.
Yeah.
And that's amazing.
Yeah.
In terms of perovskite is very thin, and also the caveat has been changed to glass instead of lead. And that is a big improvement on this thing.
Yeah.
And he is hoping that it should be commercialized in a few years. I would like to know your opinion, because calcium arsenide and calcium indium arsenides have been going on a long time.
Yeah.
And also I would like to have your opinion about the cadmium telluride, which was very good in the few years back.
Yes.
Now it is dying.
It's dying, that's right.
And the same thing is the dye-sensitized thing.
So, again, let me just talk about the new approaches using perovskites, using organic. You see, they're quite good ideas, but if you look at them, see, as you're quite right, as you can see, University of Linz here, yeah? So you see, it's gone up, start with 4%, very quickly it went to 12%, you see. The problem they have, with any device, they can work perfectly in the condition in the lab. Take them outside is a different matter. You take, for example, the organic, the problem they have is about, for example, humidity, for example. They degrade so quickly. You see, you have to encapsulate them. And then if you add another process, then you're going to use the cost and you have a problem. So this is the major problem, how you can really make them survive for a long time. Under different conditions, you see. If you look at these 3-5 semiconductors that are in space, one of the things you can think of is all about the radiation. You know, radiation in space, you got all kind of gamma rays, God knows what rays you have, and this material system have to be really, resistant to this radiation. All these can never be, for example, used in this kind of, even silicon is not, it's very prone to radiation, and it can degrade so quickly, because by, radiation, for example, you create defects. And by creating defects, what it means, those electrons and those positive charge you created in order to store them, they are practically trapped by this defect, and then you lose it. So you have to think what you're going to use them in terms not to degrade so quickly. And this is why there's still a lot of research both on perovskites and the organic, you see, because they're still not stable. So this is they might find a small niche where you can have small, in watches, for example, or something. But I think if you're going to put them on top of your roof, that's going to be very challenging for the, well, at least with what the technology is now. You say cadmium telluride, although it hasn't got the same efficiency as silicon, cadmium is a really nasty material system. You say, so it's toxic. So if you try to avoid anything which is toxic, that's a real point. And that's what I think probably, it has decreased quite a lot because of the toxicity, you say, of the material system. Perovskites actually, because now people are growing them with different methods. Not, they're using actually even, molecular beam epitaxy as well to grow this material system. So I think there is a big scope. You see, just time tell. You see, even for silicon, as you can see, which is very well-established materials, but there is some inherent problems where you cannot solve, just by. So that's what you have to play with the different concepts. Yeah. You say, so there are, maybe the things they don't tell you about this material system, because there are many concentrating on the efficiency. All they are, worried about, they don't look what is actually happening in the device. They do this, do that, they don't improve the efficiency, that's what I tell you. But you have to study actually this device in very details, and one of them is the defect. Generating defect will kill any device, even this laser. This laser, if it has got a lot of defects, what I call them electrically active defects, they will kill this laser. You see? So defect is a major problem in these devices, you see, which have not yet been studied, to be honest with you. 3.5 silicon, people have been studying this defect for a long time. This is a new material system. They still have some, a lot of people have to investigate this, how to improve them even further, you say.
Well, 2 years back, I'm sure you read about a paper in the solar agency by the German scientists. And they were doing the multijunctional silicon concentrator tandem effect.
Yeah.
And the increase to volumes.
Well, I it's a good point actually, because I didn't touch on that one, but just let me just see if I can show you this. Look, remember here, this diagram is very important. Look, one of these energies is 1 eV, yeah? Okay, it's very important, but look at the visible. Yeah, and let me just tell you why. Let me just see if I can. Okay, I am not sure if you can see it or not. Okay. Can you see this? So remember what I said before, when you stack materials one on top of the other, one thing you have to make sure is they got the same size of the crystal. You quite rightly look at silicon here, it's this size. You don't find many semiconductors which have got the same size as silicon. There's one, it's gallium phosphide. Can you see gallium phosphide here? It's here. So this is what we call the junction, and we're working in Nottingham on this material system, silicon and gallium phosphide, because it's just 2 junctions. And hopefully, this could be actually good as the 3 junction or even the 4 junction. Because this is really tuned for the 1 eV, this is really for the visible. You see, so we can stack them together. You see, ideally, we want to do everything on silicon, because silicon nowadays is 18-inch. It's a huge. But unfortunately, it's finding the right material to stack it on top of each other. That's the biggest challenge. But the solar cell, which is still a lot of big challenge, is we are looking at this material system, is gallium phosphide on silicon. Because you got the same lattice constant, and you got those energies are really well for the energy spectrum of the solar energy.
Okay, we'll take the final. There's another. Thank you. Well, we'd like to show our appreciation to Professor Henini. I'd like to invite Mr. Nathan Henderson to thank him formally.
Thank you very much.
Please meet Nathan.
Morning, everyone. Professor Henini would like to thank you on behalf of the Faculty Organizing Committee, all of us here in the audience, for giving an amazing talk on next generation devices for solar PV. One of the things we've heard so many times over the last 2 days is the importance of materials research for meeting the issues that are present in society, and the importance of energy considerations, because energy is a big thing now and will be into the future. And your talk brought the two of them together perfectly and showed the nexus between these two important areas of research. So we have a little token of our appreciation. We hope you enjoy your short visit to our faculty, to our university, and of course our beautiful island.
Hopefully this won't be, this is the first visit. Hopefully
The
there will
first
be
of many.
something, you know.
All right, so thank you again.
Thank you very much. Thank you very much indeed. Thank you, that's very kind of you. Thank you very much. Thank you. Thank you very much.
Thank you all for your attention and for your participation. We'd like to end this session now. There is coffee and snacks provided on the outside, and I hope that you will stay. Pardon me. I'm being reliably informed that lunch tickets are to be collected by the desk just outside here by the end of the first break at 10:30. So we will take our coffee and get back to the rest of the sessions for 10:30. Thank you.